everyone and welcome to EconoQuest. This is demo 2 of econometrics. Today's our topic is simple linear regression and decomposition of sum of squares. In this demo, we are going to look at the simple linear regression model in matrix form, and we will use the concept of projection matrices. Okay, so first consider the regression equation y1 equals to b naught plus b1 x1 plus b2 x2 till bk xk plus an error term epsilon 1. Okay, this is the equation corresponding to data points y and x1 till xk. Okay, this is one regression equation. Now suppose you have t observations on both y and x. In that case, you will have t regression equations, right? One equation corresponds to y1, second equation corresponds to y2 till yt. Okay, so in this system you will have t equations, right? And these parameters b naught b1 till bk, you will have k plus 1 parameters, right? So please note that we have to define relation between y and x's in all of these t equation using the same parameters b naught till bk, right? हमें इन सब रिग्रेशन इक्वेशंस के अंदर जो रिलेशंस को एस्टैब्लिश करना है बिटवीन वाई एंड एक्सिस, हमें उन रिलेशन को एस्टैब्लिश करने के लिए सेम बी नॉट बी वन बी टू बी थ्री टिल बी के का यूज़ करना है. Okay, so if you write this system in matrix form, your system will look like this. On the left hand side, you will have y vector, right? Y is in column vector form with t into 1 order. Okay, on the right hand side, you have matrices of x. This is the matrix of x data points. This is the column vector of your parameters, and this is the column vector of your error term. Okay, if you write this in matrix form, you will write this as b equals to x times b, y equals to x times b plus epsilon. Okay, so let's note down the order of these matrices. So your y matrix is of t cross 1 order, right? Your x matrix is of t cross k plus 1 order. Your b matrix is of k plus 1 cross 1 order, and your epsilon matrix, the vector of your error terms, is of t cross 1 order. Okay, so this is your regression equation in matrix form. Now we will look at the geometric formulation of this regression equation. We will see how can you represent this regression equation in geometrical form using vectors. Okay, so let's say this y vector is your column vector y, ठीक है, in some space in Rn. ठीक है ना? इस जो ये y वेक्टर है, इसके एलिमेंट्स कुछ भी हो सकते हैं, कितना भी नंबर हो सकता है. वी हैव t क्रॉस 1. ऑर्डर, तो आपका जो y वेक्टर है वो आर टी प्लेन में होगा. ओके, एंड वी represent this X matrix as a plane. This plane is the subspace. This plane is the subspace spanned by the column of matrix X. Okay, आपका जो X मैट्रिक्स है उसके कॉलम्स आपके कुछ इस तरीके से दिखाई देंगे आपको. These are the columns of your X matrix. Okay, now आपका जो सबस्पेस होगा जो ये कॉलम स्पैन करेंगे, ठीक है, वो एरिया जो आपके एक्स मैट्रिक्स के जो कॉलम्स हैं वो बनाएंगे, वो एरिया आपको आपका डिफाइन होगा इस प्लेन से जो ब्लैक से ड्रॉ किया हुआ है इस फिगर के अंदर. ओके, दिस इज द सबस्पेस spanned by columns of matrix X. Okay, and all of your X data points lie on this plane. These are your axes. Okay, so what we do in the regression, when we do the linear regression and when we estimate the parameters B hat, what we do, okay, so we try to explain this vector y which is not on this plane spanned by matrix X. Okay, this y vector is not on the plane, it is somewhere else. So we try to find out how this vector y will look on this plane spanned by the columns of matrix X. ओके, हम ये देखने का ट्राई करेंगे कि अगर हम इस y वेक्टर को इस x मैट्रिक्स के प्लेन पे देखें तो वो किस तरीके से दिखाई देगा. ठीक है, दिस इज द कॉन्सेप्ट बिहाइंड द लीनियर रिग्रेशन मॉडल. ओके, सो in simple words, what we are trying to see the shadow of y on this plane. Okay, हम जो y वेक्टर है उसकी शैडो को देख रहे हैं कि जो ये प्लेन है आपका जो x मैट्रिक्स बना रही है, इस प्लेन के ऊपर आपका जो y मैट्रिक्स है उसकी शैडो किस तरीके से दिखाई देगी. ठीक है, दिस इज द कॉन्सेप्ट ऑफ प्रोजेक्शंस इन लीनियर अलजेब्रा. Okay, and the basic idea behind the simple linear regression model is that we try to minimize the error term, right? आपका ये जितना एरर टर्म छोटा होगा उतना ही आपका जो y है वो इस प्लेन के क्लोज होगा, राइट? अगर आपका y इस प्लेन के ऊपर ही लाई करता देन वी हैव द परफेक्ट रिलेशन. उसमें उस केस के अंदर आपके एरर टर्म्स एग्जिस्ट नहीं करते, राइट? बट इन दिस केस आपका जो y वेक्टर है वो प्लेन के ऊपर लाई नहीं करता है. योर y वेक्टर इज अबव दिस प्लेन स्पैन्ड बाय योर वेक्टर x. ठीक है, वेक्टर्स ऑफ x. सो इन दैट केस हमारे पास जो सेकंड बेस्ट पॉसिबल ऑप्शन है वो है टू मिनिमाइज दिस डिस्टेंस बिटवीन योर वेक्टर y एंड दिस प्लेन. ओके, एंड when we look at the shadow of y on this plane, we will get some vector x multiplied b hat. Okay, so this unit x multiplied b hat, this is the value of y on this plane. Okay, so x b hat is the shadow of y on the plane spanned by matrix X. Okay, and this E is the distance between Y and this plane. Okay, and when we estimate this B hat parameters, in the case in which we minimize this distance between vector Y and this plane, then we have our blue estimators, best linear unbiased estimators. Okay, so this is the idea and this is the geometric interpretation behind our blue estimators and simple regression model. Okay, so now we will look how to estimate our parameters. And one more thing before proceeding, let's look at the figure again. Okay, if you notice that we have to minimize this distance between y vector and the plane, right? And this is a common fact that the minimum distance is always the perpendicular distance, right? If you find out the minimum distance between a plane and a vector, then this E vector, this E distance should be perpendicular to this plane. ओके, जब हमारा वेक्टर है उसके बीच का जो डिस्टेंस जब हम परपेंडिकुलर मेजर करेंगे 90 डिग्री से मेजर करेंगे, उस केस में आपका मिनिमम डिस्टेंस निकल के आएगा. ठीक है. सो इफ वी लुक एट and we are going to use this concept that the minimum distance is always perpendicular. Okay, the distance between vector y and the plane is minimized when vector E is perpendicular to the plane, right? That is, vector E is perpendicular to every column of matrix X. Okay, in mathematical notation terms, what does this mean? It means dot product of error vector and columns of X must be 0. This is the property of dot product. Okay, so in this case, even dot first column of matrix X plus error term 2 dot second column of matrix X plus, and this will go on till error term T dot last column of matrix X. This should be 0. Okay, and this is nothing but the dot product of transpose of X matrix and your error term vector. Okay, now your error term vector is y less x dot beta head. Okay, so you need to substitute this value here. Then we will get something like this. And when you rearrange this equation, you will get this, and from here we can get our beta hat. Okay, your beta hat will be x transpose dot x inverse dot x transpose y. ओके, हमने क्या किया यहाँ पे, x ट्रांसपोज x से प्री मल्टीप्लाई के इन्वर्स से प्री मल्टीप्लाई कर दिया अपनी लेफ्ट हैंड साइड एंड राइट हैंड साइड को. ओके, सो in the simple linear regression model, you get some normal equations, right? So in matrix form, this equation represent our normal equations. Okay, and this is our beta hat is the vectors of our parameters. So now let's look at the figure again, and you will see that we can use the addition rule of vectors here, right? To reach this y vector, we can start from this point and we can follow our vector x dot b hat. Then we follow this epsilon vector in the direction of y, and we can reach our y vector, right? So now we will see how we can write this x dot b vector in terms of y and this e vector in terms of y, and there is a simple way to do this. Okay, so if let's say this is our star equation, if you multiply star by x, okay, you will get the value of x beta hat, which is equals to x time this star equation. Okay, so this is the value of your x beta hat. Okay, we define our x beta hat in terms of y. Okay, in similarly we can define this epsilon vector in terms of y. This epsilon vector is nothing but y less x beta hat. Okay, if you put the value of x beta hat in this equation, you will get this. Right. So if we take y common from this equation, you will get identity matrix less this matrix. Right. So now you can see that we have defined our epsilon vector in terms of y, right, and we have defined our x beta hat vector in terms of y, right. So now we can write by as summation of this equation and this equation. Okay, and let's define x transpose x inverse as P matrix, right? So in that case, you can define epsilon as identity matrix minus P matrix times y, right? So by redefining in this way, your y vector will become P dot y, because this part is your P vector, right? So P times y, and this is your I times P. I minus P y, right? So we have redefined our y vector as sum of two vectors, two different parts. This part is nothing but x beta hat, and this part is nothing but your epsilon, your error vector, right? So this P matrix, so this P matrix is a special kind of matrix which with which if you multiply y, you will get image of vector y on the plane. Okay, therefore we call this P matrix as the projection matrix. Okay, so this P matrix is a special kind of matrix, राइट आपने y को इस P मैट्रिक्स से मल्टीप्लाई किया, तो जब आपने मल्टीप्लाई किया तो उसका आंसर क्या आया? P की इमेज, y की इमेज उस प्लेन पे कैसे दिखाई देगी? ओके, एंड जब आपने y को मल्टीप्लाई किया इस i माइनस पी मैट्रिक्स से, तो आपका आंसर आएगा योर एप्सिलॉन, ठीक है, द वेक्टर विच इज परपेंडिकुलर टू द प्लेन. ओके, So this is, and if you multiply vector y with I minus p matrix, you will get the image of y on plane perpendicular to the plane spanned by matrix X. Okay, so this P and this I minus P matrices are the projection matrices. Two different kinds of projection matrices. Okay, now note both P and I minus P matrices are idempotent matrices. Okay, it means P dot P equals to P square equals to P, and I minus P times I minus P is equals to I minus P. This is the property of idempotent matrices. Okay, this is where idempotent matrices come into picture in the linear regression model. Okay, and idempotent matrices also have many applications when we do the hypothesis testing, that is statistical inferences about our parameters. In those cases, idempotent matrices also come into picture. Okay, so now we will look at the decomposition of sum of squares. There are so many ways to look at this decomposition. Okay, and in this video we will discuss 3 cases in which you can look at this decomposition of sum of squares. Okay, so our first method is going to be geometrical method. Okay, so let's look at the picture again. In this picture, we have our x dot b hat matrix, right? We have our error term vector, and we have our y vector, right? These 3 vectors are forming an right angle triangle. These 3 vectors are forming a right angle triangle, right? So we can use the Pythagoras theorem in this. Okay, the square of this vector plus the square of this vector is equals to the square of y vector, right? This is the Pythagoras theorem. So if we use the Pythagoras theorem in our picture, then we will get y transpose y, which is equivalent to y square, is equals to xb hat square. This is equivalent to xb hat square whole square plus error term vector square, right? Using Pythagoras theorem. So if you simplify this, you will get something like this, right? Your left hand side is total sum of squares. The first term on your right hand side is your explained sum of squares, and the second term is your residual sum of squares, right? So what this equation is saying is that the total sum of squares of your y vector is your left hand side. Okay, so this first is the variations. This first term is your variations in y, which is explained by your x data points, and this residual sum of squares are your variations in y, which is not explained by your x data points. Okay, so this is the first method of looking at the decomposition of sum of squares. Now we will look at the second method. Right. So in the second method, we have our y is equals to py plus I minus py, right? And we have to find out the value of we need y transpose dot y, right? So what you can do is pre-multiply both sides by y transpose. So you will get y transpose y, which is your y square, y transpose dot py plus y transpose I minus p dot y. Right, when you simplify this, you will get exactly b hat x transpose x b hat plus e transpose e, when you will put the values of p and I minus p here. Okay, your value of p is equals to x transpose x inverse x transpose. Okay, our third method is we have defined our xb vector as py, right? And our error term vector as I minus py. But we need the square of these vectors, right? And we need to calculate y square, which is y transpose dot y. It is equals to py plus I minus py transpose times py plus I minus py. Right? When you simplify this, you will get y transpose p transpose plus y transpose I minus p transpose using the formulas of rules of transpose. And here I am using the rules of matrix multiplication. Here I have used the rules of matrix multiplication. Okay, so since P and I minus P are idempotent matrices, they also have this property that P transpose P is equals to P. So when you will simplify this, you will get Y transpose PY plus, since P and I minus P matrices are perpendicular to each other, their multiplication will result in 0. Okay, so both of these terms become 0. So you are left with first term and last term. And your last term becomes Y transpose times I minus P times Y. Okay, and when you will put the value of Y, you will get B hat X transpose X inverse B hat plus so again your left hand side is total sum of squares is equals to your explained sum of squares plus your residual sum of squares. So this is three methods of looking at the sum of squares. Okay. So these will becomes beta t. Okay, so this is the methods of looking at the decompositions of sum of squares using matrices and the concept of projections.